So we're doing chapter 5, nullclines and equilibria, first section in chapter 5. So let's take a look at our problem here.
We're in week 8 already.
Yep. Yeah, next week's off. All right, so here's our system. How do we know it's not linear? Name something not linear.
Another one to ask. I'm sick.
Okay.
I can't do
We have
math.
x squared. We have x squared times y. We have y squared. That's just in the first line. I also have an x squared here and an xy. That's nonlinear.
No, it's
So
not.
stuff can happen to t. T could be sine t or t squared, but y is supposed to be just y prime, x is supposed to be xx prime. So this is our system. So it's a pretty complicated looking system if you think about it. So the derivative of x with respect to t is this, no t stuff. Derivative of y with respect to t is this, no t stuff. That's pretty weird, but it's not it's not a matrix problem. I can't express it as a matrix because of that x squared and that y squared. Remember, for a linear, you have x to the first y, the first thing you have a matrix times xy.
Right.
So it's nonlinear. Well, let's see what we can do with it. It turns out you can do a lot with this thing. So what we do is we graph the factors. So this is the graph of 9 minus x squared minus y equals 0, otherwise known as, I'm going to write the y right here. Y equals 9 minus x squared. That's this guy. Okay? This guy here is going to be that line, y equals 3 minus x. So we care about when the factor is 0. That's why I'm setting each factor equal to 0. X equals 0 is the y-axis. This is x equals 0. And y equals 0 is the x-axis. Okay?
Yeah.
So we're going to want to keep that information. When I go to the next slide, I hope it's still in the same position. Let's see if it is. Oh, just a second. Am I still recording? Yes, I am. Yes, I pressed the wrong thing. I pressed enter on my laptop. Here. So there we go. Let's mark the direction field arrows on these guys. Okay, so here we go. When I have, let's start right here. Y equals 0 gives me dx dt equals 0. What kind of arrow has dx dt equals 0? A vertical arrow or a horizontal arrow? We're going to draw a direction field that it's vertical. That's right. The change in x is 0. No x change. So that means that I have up arrows and down arrows on y equals 0. So y equals 0, that's the x-axis. Y equals 0 has up and down arrows. Let's see how we find them. It's really easy. The sign is going to come from putting 0 in for y here. So I have dy dt equals x times 3 minus x minus 0. So when x is 0, there is a change. I get a 0 there. When x is 0, and when x is 3. Now, when x is bigger than 3, when x is 4 for x equals 4 gives me a positive times a negative. That's a down arrow, because I have 4 times 3 minus 4 for dy dt. dy dt is negative. So there's a down arrow here. I guarantee I'm going to get an up arrow here. Let's put a 2 in. X equals 2. And I get a 2 times 3 minus 2. That's positive. That's an up arrow. Okay? I'm certain I'm going to get a down arrow from here for the rest of its life. So let's give it a try. When I try negative 2, x equals negative 2. I'm going to have negative 2 times 3 minus negative 2. That's a 5 times negative 2. That's negative. That's a down arrow. This is what usually happens. The places where I have zeros are places where the arrow changes. So I have an up, a down, and a down because I crossed these guys here. These guys are going to be equilibria because it's a place where y is 0, or sorry, dx dt is 0 and dy dt is 0 here and here. So I have an ordered pair of constants that satisfies the differential equation. So that means that I have an equilibrium. The equilibriums are so far 0, 0 and 3, 0. Let's keep score of equilibriums. All right, I'm going to erase and do another one. That was just the horizontal axis. I've got 3 more nullclines. While I'm doing verticals, I do the other factor, and that's the y equals 9 minus x squared. So that has vertical arrows on it as well. Now, let's see.
Where'd you get y equals 9 minus x squared?
This guy.
So you plugged in a 0 for y?
I'm treating dx dt is equal to 0.
Okay.
So dx dt is 0. How? Well, I'm letting 9 minus x squared minus y equals 0. So I rewrite it as y equals 9 minus x squared. So I'm going to try points on this parabola.
But wait,
Go ahead.
The y that's in front doesn't come into the equation?
Already, we just used that one. I erased it. We used y equals 0.
But I'm saying, like, right here, this y, like, you got this from here, correct? Why is this one not included in the whole thing?
Because I'm going to take one factor at a time being 0. I just did this
Okay.
factor being 0.
Okay,
And this factor being 0 means this is 9 minus x squared.
okay.
I don't care about it. I have a 0 right here. Whether this factor is 0 or not doesn't matter because the whole thing is 0.
Okay.
So when I do when I do y equals 9 minus x squared, sticking 9 minus x squared right there, this whole thing is 0. Doesn't matter what the y
Okay,
is.
okay.
I have 0 times the rest.
All right. No, I
But
understand.
now I have 9 minus x squared, and I wonder how it does with up and down arrows, because it's a place where dx dt is 0. So I get up and down arrows on this curve. Which are the ups and which are the downs? Okay? So here's what I got to do. I have y equals 9 minus x squared, and I have this whole piece of arc here. I can choose any ordered pair I want. Let's say I choose, let me get this a little bit more accurate. Let's say I choose 2, and 9 minus 4 is 5. So here's the point 2 comma 5. I'm just picking it out of thin air, because whatever I get, it's going to apply to this whole piece.
Mhm.
Not sure about up here, because this is a place where when x is 0, y is 9. Oh, that'll make the top thing 0. I don't think that's an equilibrium, because it just makes the top 0. This guy's an equilibrium, I already know it. This could be an equilibrium, because it's a slanted line with this curve. That'll be an equilibrium when we get there. I might have the same kind of arrows writing this whole thing. So 2 comma 5, in the lower one, dy dt is going to be 2 times 3 minus 2 minus 5. That's negative.
Mhm.
So I have a down arrow all in here. I think it's down arrows all the way, because this point, 0, 9, only makes this piece 0, which I'm already treating as 0. It doesn't make that 0. So if I put 0, 9, let's just try 0, 9. 0, 9. If I try it in here, I bet I get a negative. So I'm getting a 0. Oh, I'm getting a dy dt equals 0. Oh, because x is 0, 9. Okay, I'm getting a 0. So this is that's an equilibrium. 0, 9 makes dy dt 0 because of the x equals 0. Okay, so I got an equilibrium there. I bet this arrow goes up. Let's try this guy. So I come over here and I try a point like negative 1, 8. Negative 1, 8 in this expression right there. So I have negative 1, 3, minus negative 1, minus 8. Let's see, that's going to be 4 minus 8 is negative 4,
Positive.
minus negative 4 is 4, it's positive. As expected. I got it up there, I bet money that's a down, because I passed an equilibrium.
Mhm.
So you have to do the slanted line, you have to do this vertical line. You don't have to do all this by hand because a computer can do it. So let's go to the computer and see if it matches what we had.
So you want to add up there 0, 9 as another equilibrium?
We would have to go through what we just did with this line 2 more times, writing the arrows. And those, because of on this side, if we have dy dt equals 0, that means my arrows go this way,
Right.
because there's no change in y. So we're expecting horizontal arrows along here and horizontal arrows along here. Okay? So if we can remember, that's along the slanted line and the vertical line, and we have up and downs on the parabola and the horizontal.
Mhm.
All right, let's go and see if the computer, because the computer can do this thing. The computer can go and give you a direction field and as long as it takes you to type it up, and that's it. So check it out. Here's the maple direction field, and you can see, oh my goodness, look at this stuff. I can see the parabola. I can see, I don't see this line, but I can see that there's a disturbance right in here. See these arrows pointing away from each other? And that'll be the point, negative 2.5. Because what happens at the equilibria is weird stuff happens. Negative 2.5 was an equilibria. We already know about 3.0. Look at 3.0. There's a mash of arrows around 3.0.
0.9 was another, I think.
0.9. 0.9's up here. Let's look for the mash around here. I've got an arrow that's going this way around 0.9 and it's going this way, but then right after it I've got arrows going like this. So something interesting happens at 0.9. I've got a complete change in personality there. But look at the rest of the way, straight horizontal arrows. Like we knew about. For the vertical line I had horizontal arrows. And for this guy, was I supposed to have vertical arrows? I think I was. I think I did. And I see vertical arrows until I get near an equilibrium. I get near an equilibrium and my vertical arrows fail. And they say, well, I don't see any vertical arrows in here. And this is really an artifact of the points that they choose. The arrows in here are going to be vertical going up. These are going to be vertical going down. It's just the arrows that they drew, the tail is where they draw the tangent at. So they didn't get anybody right on the line all the time. So I've got those kind of arrows going on. That was an up. These are now down, so you can see little down arrows here. On the parabola, we're supposed to have up and down arrows. And riding this parabola, these look like we're going to have down arrows riding the parabola here. We don't have every arrow showing, but for the parabola, I've got down arrows. And then I've got some up arrows here, which I crossed an equilibrium. And then there's this other equilibrium over here at negative 2.5, like right in here. And now I'm getting down arrows again, riding that parabola. Now for this horizontal line, or for this slanted line, it looks like I'm supposed to get lines like this and like that, because I can see them. As I cross through here, I'm getting horizontal arrows in there. And then we get these equilibria, and an equilibria is when both dx dt and dy dt are 0. So there's a negative 2.5, 3.0, 0.0. There should be one more.
0.9.
0.9. Good. 3.0 is a weird one because 3.0 gives me an equilibrium in two different ways. So I could have a real messed up little set of arrows around there if I were to zoom in using my computer. It could be quite complicated. Because it's like the pieces are fighting with each other. Which of them is more important? So here's the other thing we can do is we can get a phase portrait. Let me erase so you can see. In Maple, or in anybody's system, anybody using a computer algebra system that handles differential equations, you can get a solution. So let's observe this thing right here. I'm reading it. This is x prime equals 9 times y minus x squared y minus y squared. So I multiplied through. Then I have the y prime equals 3 times x minus x squared minus xy. So that's my system. I wanted it to graph my arrows, and here's my initial conditions. X sub 0 equals 3.5, y of 0 equals 0. So I'm at 3.5, 0. And then you can see this yellow curve here, and the reason I get above and below is because I did t negative 2 to 2. So I did time steps before. Here's negative t, following those arrows, and then positive t, coming across like that. So that's a solution near an equilibrium. That's what a solution curve looks like. All I have to do is tell it, what do I care about? Tell me the initial conditions. It will graph me one. Let's do one more. Can you see that yellow curve? I'm going to emphasize it for the video. So I did this time from t equals 0 to 2. So here's a t equals 0. I can tell because of the arrows. That must be times 0 here. And this curve, it comes over here, and it rides that parabola and heads down toward this guy. But what is happening is, as time goes to 10, 20, 30, I'm going to head toward this equilibrium, and I'll never quite reach it. That's what's going on. That's why it stopped short. But if I were to do t equals 0 dot dot 10, it would get closer 0.20, it would get a little closer, but it's always going to approach that sink. So this guy's a sink from this direction. I'd have to check other directions to see if it's sink from other directions. It looks like it could be a sink all the way around, and we have a way to find out. Let me show you the last slide. And that's to use the Jacobian. This thing is equal to, I had this before, 9y minus x squared y minus y squared, and this part is 3x minus x squared minus xy. The Jacobian is you take the partials. So I take the partial of this with respect to x. I take the partial of this with respect to y. Each of those guys goes here. So the partial derivative of that with respect to x is 0 minus 2x, y minus 0. Partial with respect to y, 9 minus x squared minus 2y. Do you remember doing partial derivatives?
I do, yeah.
Okay, and then the partial with respect to x, 3 minus 2x minus y. And when I do the partial with respect to y, only minus x survives. So there's the Jacobian. The Jacobian at an equilibrium gives the system, the local system. How cool is that? So let's try 0, 9. The Jacobian of 0, 9 gives me the following: 0, 9 minus 0 minus 18 is negative 9. 3 minus 0 minus 9 is negative 6, and 0. That one is, I think, two real roots, two real distinct roots. So that would be two real distinct roots. I think they're both positive, and that would mean that for the equilibrium up here, I'm getting solutions that I'm getting solutions of this form. Like in this system, I've got this point, and I'm getting curves like this. Remember?
Mm-hmm.
I'm getting one of those guys with two linear solutions, but it's only local. It's only a little bit around here, and I can kind of see it. I've got around it, I've got these little guys. I've got solutions that are riding like that. I see them. I see them. So this is a really interesting thing. Your little formula sheet applies in section 5.1. As long as I have at least one 0 entry. If I have all entries that are non-zero, I will give you what the eigenvalues are. That way you don't have to worry about the general case of finding them. But if you have at least one 0 entry, you can talk about what's going on locally around that equilibrium. So that's what makes this one so interesting. We'll get into those details in class. This guy's weird because he's in equilibrium two different ways. There's 3 curves meeting there. 2 pairs of those 3 would give me an equilibrium at the same point. So he could be a real swirly, complicated character. So we'll look at that when the time comes. Questions?
I don't have any right now.
All right, I'm going to shut it down and I'm going to post it later. Let's see how long we got. 18 minutes, that's about the max.